I would recommend trying to figure out the answers to these 3 questions right here by looking at those vocab words and using that table to help you out. That's what we did in class. We did that with a partner, and then we went over the answers. So if you tried these, the probability of rolling an even number on the number cube, even numbers are 2, 4, and 6. So there's 3 even numbers out of the 6 numbers on the cube. And then we reduce that to 1/2. The sample space of the spinner, if we look at the definition of sample space, it says the set of all outcomes. It means what could possibly happen if you spun the spinner. Well, there's 4 options here. The spinner could land on red, green, blue, or yellow. So listing out those words in the brackets, because we're writing a list, red, green, blue, and yellow, that's the sample space. The sample space for the number cube would be the numbers 1, 2, 3, 4, 5, 6, like you see right there. And number 3, the complement of rolling a 5. Well, what's a complement? It's everything not in an event. So if our event is 5, that means that everything besides the 5 on the cube would be a 1, 2, 3, 4, or 6. So we'll write that as a list in the curly brackets. And that's the complement. My fancy definition of theoretical probability is what should happen in theory. Like if you flip a coin, you should get it to land heads up half the time and tails up the other half of the time. So it's defined as your favorable outcome divided by the possible outcomes. So like landing heads up would be, there's one side that's heads, and then there's either heads or tails, so that'd be 1 out of 2 for probability, in theory. So let's try example 1A. We have a CD with 5 upbeat dance songs and 7 slow songs. We want the theoretical probability that you randomly put a song on and it's an upbeat dance song. So upbeat dance song is our favorable outcome. There's 5 of them. And if we add the 5 and the 7 together, we'll get 12 because there's 12 songs on the CD. We can't reduce 5 over 12, so that's the answer. On 1B, we have 2 number cubes we're going to roll at the same time. One of them's red, one of them's blue. It's a fair number cube. That's what it means by all numbers are equally likely. It's not a lopsided or odd-shaped cube. We want the probability that the sum of the 2 numbers is 10. So we can figure out how many possibilities there are. We could either count up the number of trials that are listed right here, or we could use the fundamental counting principle. Since there's 6 sides on the red cube and there's 6 sides on the blue cube, we can multiply those together and get the total number of possible outcomes. So we know we're going to be dividing by 36, and we just have to figure out how many are going to add up to 10. So they're already circled. If you get a 6 and a 4, a 5 and a 5, or a 4 and a 6, then they'll add up to 10. So 3 out of 6 is the fraction, and that reduces to 1/12. Next, what's the probability that a coin lands on tails? Well, one of the sides is tails out of the 2 possibilities, so 1/2 is the answer. And what about the number cube is going to land on a 6? Well, there's 1 6, and there's 6 sides, so 1/6. I don't know if you've ever played Battleship before, but this is what the board looks like right over here. And we're going to figure out the probability that the first shot misses all the targets. If you miss all the targets in Battleship, it means that you didn't land on one of those gray ships. It means you landed somewhere in the water. So if we look at the problem, it says there are 100 holes on the grid. So we know there's a possible 100 places that we could guess. We want the probability that it misses all the ships. In other words, it's going to land somewhere out here in the blue. So we have to figure out how many of those squares are not covered up by the ship. We can either count them up by looking at that grid, but that'd kind of take a long time, or since we want the number of holes not covered, we can add up the number of holes that are covered. If we add 2, 3, 3, 4, and 5, that gives us 17, and the leftovers will not be covered. So if we do 100 minus 17, that gives us 83 uncovered spaces, and that doesn't reduce, so there's an 83, if we write that as a percent, 83% chance that you're not going to hit a ship on your first guess in Battleship. The next question is, what's the probability that your first shot, so none of the spaces have been guessed yet, actually hits a target? Well, 17 of the spaces actually have a ship on them out of the 100. So 17 out of 100, or 17%. So all you can do in Battleship is either hit a target or miss the target. You can't really do anything else. So those two events are complements of each other. What do you notice about the 83 and the 17%, or the 83 over 100 and the 17 over 100? If you add them up, if you combine them together, you get 100 out of 100, which is 1, or if you add the 83 and the 17%, you get 100%. This is the rule of complements. Whenever you have two complements, when you combine their probabilities, it has to equal 1, because nothing else can happen. Just like if we think about the heads and tails. You have a 1/2 or 50% chance of getting a coin to land on heads, and a 1/2 or 50% chance of getting a coin to land on tails. And when you put them together, it equals 2 over 2, or 1, or it equals 100%, because there's nothing else that could possibly happen. Next, we have experimental probability. This is what actually happens if you run a bunch of trials. So the little formula, the probability of an event happening, is the number of favorable outcomes that you observe, favorable outcomes, divided by the number of trials you do. So if we flip a coin 10 times and we get it to land on heads 6 times, then our experimental probability would be 6 out of 10. So the book rolled an oddly shaped number cube 100 times, and they put the results for how many times each number came up in this graph. So just by the looks of it, it looks like it must have been pretty easy for the cube to land on a 5, because there were a whole bunch of 5s and 2s. So let's figure out the experimental probability, so according to what the book did, of rolling a 3. Well, it looks like it landed on 3 16 times. So 16 out of the 100 rolls, and when we reduce that, if we divide them both by 4, it reduces to 4 over 25. Always put your answer in the lowest form. Next, the experimental, so according to this graph, that they rolled a perfect square. Well, the numbers 1 and the numbers 4 are perfect squares because when you square root them, you do not get a decimal. So it landed on 1 17 times, and it landed on 4 11 times. So all together, that would be 28 times it landed on a perfect square out of the 100 rolls, and that reduces to 7 over 25. Last, the experimental probability of rolling a number other than 5, so all the other ones except for the 5. What we could do here is find the complement by taking all the rolls and subtracting the number of times it did land on 5, which is at 22. So if we subtract 22 from the total, that leaves us with 78 on other numbers, and so 78 out of 100, that reduces to 39 over 50.